So welcome again. Today we'll be discussing lecture 16, which is on coreference resolution. This will be this is the agenda for today's study group. So in lecture 16 is all about coreference resolution. We'll get started with what exactly is coreference resolution, and then we'll see where exactly we can use coreference resolution and how it helps us. And there is something called mention detection, which is part of coreference resolution. We'll see what that is. And there are like different kinds of coreference resolution models, which are like traditional models. And then we have neural network driven coreference resolution models as well. We'll touch upon that. And then there's something called Hobbs algorithm, which is a rule-based coreference resolution model. And mention pair and mention ranking are two other kinds of resolution models. So these are all the things that we'll be going through quickly in this lecture. So what exactly is coreference resolution? So when we have a sentence like this, different words in this sentence might refer to different entities. And also some of the words in this sentence here might refer to a word which has already come before it or comes after it. So there is a possibility for both to happen. So coreference resolution helps us in identifying these kind of coreferences between the words. These are actually called mentions, and mention is nothing but a word that refers to some real world entity. Like here, Barack Obama is a mention, and it is actually referring to some person in real life. Similarly, Hillary Clinton is another mention, and we have several other mentions here. Let's see what they are. So here it is. All these words that are marked in blue are all examples of coreference resolution mentions in this sentence. Barack Obama is a mention. We have Hillary Rodham Clinton. His Secretary of State is also a mention. And we have another mention here called Monday, which is a day in the week. And then we have some other mentions here. So mentions help us in figuring out the coreference resolution. And how they help us with that is that first we have to figure out all the mentions in the text like this. Here we have marked all the mentions. And among those, we have to filter and say which mentions actually co-refer to each other. So here we had all these mentions, and now when we filter them using coreference resolution using mentions, we have Barack Obama, his, and he. So all these three words are referring to the same entity, which is Barack Obama. So this is how mentions can help us in coreference resolution. So this is one example. And then we have another mention here. We have Hillary Clinton. Secretary of State also refers to Hillary Clinton. The pronoun her also refers to Hillary Clinton. And the words she, First Lady, are also referring to the same entity, Hillary Clinton. So these are all mentions which are referring to the same entity. So far it looks good. But how trivial or how trivial is this task, coreference resolution? Not trivial at all. In fact, it is believed that solving coreference resolution it's like one of the steps that would mean that we have proper AI, which is why it makes coreference resolution a very tough task. This is an example sentence. A couple of years later, Vanaja met Akhila at the local park. Akhila's son Prajwal was just 2 months younger than her son. So here, as we can see, we have so many words. We have so many people's names here: Vanaja, Akhila, Prajwal, Akash. So when we are reading a sentence like this, for humans, it is kind of intuitive to understand what exactly the word in the middle of a sentence is referring to. Like, for example, the word her. We have a sentence here: Akhila's son Prajwal was just 2 months younger than her son. So what does her refer to here? It is actually referring to Vanaja. So even for us, like we have to go back and figure out who exactly the pronoun her is referring to here. So while it seems like an easy task for us, for a machine or a computer to do it, it's not that trivial. We'll see in some of the examples why it's really hard task figuring out coreferences. So what are the applications of coreferences? One is full text understanding, information extraction, question answering, summarization. So given an example, like he was born in 1961, if this is a sentence, we would definitely want to know who the word he is referring to. So that to know or understand who exactly he refers to here, we need to know to what entity it is actually referring back to. So text understanding is one application of coreference resolution. And another one is machine translation. So different languages have different features. Like there are languages which doesn't have pronouns at all. So when you're trying to do machine translation from one language to another, from one language that uses pronouns to another language that doesn't, now that it becomes critical to figure out how the how the coreference works there. So, which is why in cases like this, we see that there is some sort of correlation between here the job and the gender. So she is a nurse, and we have these kind of examples here, whereas the source language doesn't really have the pronouns, where the pronouns are dropped. And another application of coreference resolution is dialogue systems. When a dialogue system takes some query or some request from the user, and then it has to send a response. Now, to send a response, it has to properly understand what exactly the user's query is or the user's request is. When the user says something like book tickets to see James Bond, the dialogue system has to understand that here James Bond entity, it's a mention, and the action book tickets is different to this James Bond. So these are the kind of the dialogue systems need to understand how the entities or the mentions are related to each other. So there are two steps involved in coreference resolution. One is detecting the mentions, as mentioned. So as we have seen in the previous slides, mention is nothing but all the words that refer to some real-time entities. So here, given a sentence like, I voted for Nadar because he was most aligned with my values, she said. So here, as we can see, all the words that are enclosed in blue braces are all mentions. So now the first part is like detecting the mentions, which is comparatively easier task to do than to cluster the mentions. So what exactly clustering the mentions mean? So here, as we can see, we have two words here, Nather and he. And by clustering the mentions, we are saying that these two words are correlated to each other. Similarly, the words I, my, and she are all referring to the same entity, who is, they're all referring to the same entity, she. So there is no name here, but they're all referring to some person here. And from the pronoun, it is clear that it's a female. So by clustering the mentions together, we can figure out the coreferences. So coming to mention detection. So mention is a span of text referring to some entity. So the span of text could be one word, two words, or it could be multiple words. There are different kinds of mentions. One is pronouns. Like I could say something like, Alex is not in the class. He's in the playground. Now, in second part of the sentence, it is clear that the word he is referring to the person, Alex. And similarly, we have named entities as well, people, places, etc., as we have seen in the previous example with Barack Obama. And we have noun phrases as well. These are the kinds of mentions that needs to be detected. So we can use a part of speech tagger to detect the pronouns. And for detecting the entities, we can use something like named entity recognition. And then we have, we can use a parser for detecting noun phrases as well. So mention detection is not an easy task to do. For example, when we say something like it is sunny, what exactly the word it is referring to? So sometimes there might be examples where it could refer to something, but there could also be sentences where it doesn't really refer to something concrete, like it is sunny and every student, no student, the best donut in the world. So these are all some examples where the span of text, the words are not really referring to something specific in the real world. So that's where mention detection gets very tricky. So how do we deal with the bad mentions? So one thing we could do is we can train a classifier that kind of filters out any bad mentions. For example, like what it could do is we can get started with taking all the mentions as the candidate mentions, and then we do the coreference. And once the coreference is done, we discard all the mentions that are not really coreferenced with anything else. So that's one way of getting rid of the bad mentions. So as we have seen, what we do is we have these different components that help us with mention detection. Like we use POS tagger for parts of speech detection, and then we have named entity recognition for detecting entities from the text, and then we have a parser as well. So this gives us a pipeline kind of a system in place. So instead of that, it is also possible to combine both mention detection and coreference resolution into an end-to-end model. So that's what the current systems are trying to do. So here's some linguistic stuff. So coreference is when we have two mentions that are referring to the same entity. So we have some sentence like this: Barack Obama traveled to go. We have some text there. So here we know that Barack Obama is an entity. And here is an example. Barack Obama said he would sign the bill. So we know that Barack Obama and he are like two mentions in this sentence, and these two are actually co-referring each other. So Barack Obama is called antecedent, and he's Anaphora. So Anaphora is actually the word that refers back to something. So whenever we have a coreference, we need at least two words. So in this case, we have Barack Obama and he, and the word that comes first, the word to which another word refers back, is the antecedent, and the word which is referring to another entity like Barack Obama here, which is he, is the anaphora. So, but does that mean all anaphoric relations are coreferential? Not always. So we have an example here: every dancer twisted her knee, no dancer twisted her knee. So though we have these mentions here, they're not really coreferent each other. So just because we have an anaphora doesn't mean that it always corefers some antecedent. So that's about anaphora. What about cataphora? So well, in the previous example, we have seen that Barack Obama said he would sign the bill. So here, anaphora is something that comes next. So we have the entity here, Barack Obama, and later on, to refer to Barack Obama, the pronoun he is being used. So when the antecedent comes first and then follows, and the anaphora follows, that's one way. We may also have it the other way, where, as in this case, from the corner of the divan of Persian saddlebags on which he was lying smoking, as was his custom, innumerable cigarettes, Lord Henry Wotton could just catch the gleam of the honey sweet. So here, as we can see, the pronoun comes first, followed by the actual entity's name, which is Lord Henry. So this is another other possibility where we have the antecedent coming after. The pronoun comes first, and the real entity comes later. So these are the four kinds of coreference models that we have. One is rule-based, the other one is mention pair. Then we have mention ranking and clustering. So when it comes to rule-based approach, there is something called Hobbs algorithm. It is considered to be very naive, a typical rule-based algorithm, which works in some cases, but not all the time. So it builds some kind of tree like this, and then does the coreference resolution. But there are some problems with this algorithm like this. So when we have an example like this, she poured water from the pitcher into the cup until it was full. So now here, the word it in this sentence is referring to the mention the cup. Whereas in the next sentence, we have something which is very similar. She poured water from the pitcher into the cup until it was empty. In this sentence, the word it is referring to the pitcher. So depending on the word full and empty, we have different coreference here. So this is what makes coreference resolution very tough and tricky. It's not really easy to have a robust system in place which could do coreference resolution for any kind of text. Here is another example. The city council refused the women a permit because they feared violence. In this case, the word they is referring to the city council. And in the next sentence, the city council refused the women a permit because they advocated violence. In this example, the word they is referring to the women. So how will a machine or a program understand this subtle difference? Like we have two sentences which are very similar, both in the distribution of words, in the words that they have, and also they are syntactically very similar. Yet one word makes a difference, and the coreference also changes accordingly. So this is actually called vinaigrette schema. What vinaigrette schema does is it gives examples of text like this, and if we have a coreference resolution model in place, you can test that on this to figure out how good it is. And it is even proposed. Can you hear me?
Yeah, I can hear you now. I think you disappeared for a second.
Yeah, even for me too. Let me share the screen. Do you see the slides now?
Yes.
Sure, okay. So I was talking about vinaigrette schema. So when we have a collection of sentences like this, and we try to test our model or program on this, and if it is able to figure out these kind of differences correctly, then we can say that we have a system which is pretty good. And vinaigrette schema is even proposed as an alternate to the Turing test. Turing test is something that is used to, if a machine can fool a human by making the person think that the one at the other end is also a human, then the machine passes the Turing test. So vinaigrette schema is something which is an alternate for that. If a machine can figure out the coreferences correctly for examples like this, then we can say that they are pretty good. So this is about Hobbs algorithm. Well, it says that it will be a long time before a semantically based algorithm is sophisticated enough to perform as well. and these results set a very high standard. So in the first sentence, in the first comment here, we see that Hobbs algorithm actually does a good job for at least for some sentences, but it's not really something that could be uh, that is very good, because anyone can handpick examples where these kind of rule-driven algorithms terribly fail. So that's the problem with these kind of rule-driven approaches. So what are mentioned pairs? So here we have different clusters. As we can see, we have two words, another and he, which are in blue, and they both together form one cluster. And then we have another cluster of words, I, my, and she, and they form a different cluster. So here we have different mentions, and they are being clubbed together into different clusters as mentioned pairs. So what we do is to get these mentioned pairs, we train a binary classifier which takes every pair of mentions and says whether they are whether one is a co-referent of the other or not. For example, here we have these words here. Now we want to know what other words in the sentence are co-referents with the word she. So we can do this using a mention pair coreference model. So in this case, since it's a binary classifier, we'll have positive examples and then we have negative examples. For this example, the words I, my, and she will form positive examples. Like my and she will be one positive example pair, and similarly, I and she will form another positive example pair, whereas she and he will be will be a negative example pair. So this is how we can train a binary classifier to get the mentioned pairs. So here, these are the examples of negative examples: she and he, another and she. So once we have those examples, we'll train our classifier using cross entropy laws, and which will help us in mention pair detection. So here again, the same thing. We are forming different clusters here. So instead of simply treating that as a binary classification problem, it's better to have some sort of clustering. There is one problem with this. If A is found to be a co-referent of B, and B is found to be a co-referent of C, then A would be a co-referent of C. So going by that rule, if we have if we have these kind of chainings that happen, then somehow it means that every word is a co-referent of the other. So here, when we have something like she is co-referent of I and she are co-referring, and we know she and my are co-referring. So that would form these kind of chains where every word is somehow co-referring to the other, which is these kind of mergers are not they form these big clusters which are not really good. Okay, so what we know is that whenever we have mentions in the text, and what we try to figure out is when we have a mention, we try to get what its antecedent is. But going by examples like this, we're actually trying to form these mention pairs where every word is trying to be matched with every other word. So which is not really how it is in real time, because many mentions will have one clear antecedent, but in this case we are trying to match it with every possible word. So what we can one tweak that we can do here is that instead of training a model to predict all trying to match all the mentioned pairs, what we can do is we can train the model to predict only one antecedent for every mention. So here we have the three words, I, my, and she. And by using mention ranking, the model is expected to assign high probability to only one of the words, one of the antecedents, but not both. So that's what we see here. For the score for NA and she is 0.1. And as we can see here, it is maximum for I and she, which makes sense because I and she are proper mentioned pairs. Whereas for every other word, it has pretty low score. So we have somewhere here. So when it comes to testing, there is only one antecedent is assigned to every mention. So unlike the training where we had the same word being paired with multiple antecedents, here at the test time, the model tries to come up with one antecedent for every word, for every mention. So we have seen the probability scores that are being generated here, and there are different ways of getting the probabilities using statistical classifiers, using a neural network, and using the more advanced models like LSTMs and attention-based models as well. So this is how a non-neural coreference model works. The way it works is, it's again like what used to happen before machine learning came in is that there used to be a lot of hand engineering. For every task, there used to be a lot of hand engineered features that are formed, and then the model is trained on top of those. For example, we have a feature like this. Jack gave Mary a gift. She was excited. Now, we know that whenever we have two names here, Jack and Mary, and then we have the pronoun she. From the English grammar rules, we know that she can only refer to a female but not a male. So this could be one rule where we say that she is referring to Mary but not to Jack. That's one feature. And then there is also semantic compatibility, and then there are some sort of constraints like John bought him a car. Him cannot be John, because here we have one person's name, which is John, and then in the same sentence we have a pronoun him. But we know that him is not really referring to John, so it has to refer to someone else who was talked about before, or who will be talked about later after this sentence. And another feature or rule could be that the mentions actually refer to the most recent entity. So we have sentence here, John went to a movie, Jack went as well. He was not busy. Now, who exactly is the word he referring to? So using a feature like this, he can be made to refer to Jack rather than John, because Jack is the entity which is the closest here to the word he. And then we have some sort of grammatical rules as well. Jack went to a movie with Jack, he was not busy. So these are kind of features that the people used to come up with, hand engineer these features, and then train a model. This is how it used to be before the neural networks were used for coreference modeling. So when it comes to coreference models, just like any other neural network model, we get started with the embeddings. We have different embeddings here. We have embeddings for mentions, we have embeddings for candidate antecedents. So once we have all these embeddings, we pass them through some sort of neural network, and which would generate the scores for us. So there is another blog that I will be showing at the end of today's session, which talks more about this. So we get the embeddings for previous words, first word, last word, head word. We get the embeddings for these different combinations. The head word is considered to be the most important word, and that can be found out using parsers like the fluffy cat stuck in the tree. So here we can see that the entire sentence, the the most important mention or the entity would be cat here, and all the other mentions or entities are actually dependent on this. So we have seen how a pipeline kind of a system is used. Like we have parts of speech tagger followed by NER, and then we had several other components. Instead of that, it is possible to have an end-to-end model to do coreference resolution that uses a feed-forward neural network using LSTM, attention, and something called span. So coming to the end-to-end model, we have, let's say we have a text like this. General Electric said the postal service contacted the company. So once we have text, once we have the words, we get the word embeddings for each of the words here. So that's what we're doing here. These blue dots represent the word embeddings for the words. And then we pass these embeddings through a bidirectional LSTM. So which is kind of standard procedure in NLP. And what's different is this: we have something called span head here, span representation. So what exactly is a span? Span is nothing but a sequence of words in the sentence. So we'll see examples like this. So general is a span. General Electric is another span. General Electric said is another span. So span is nothing but a sequence of words of different lengths. So it could be of length 1, like general. It could be of length 2, like General Electric, or it could be of length 3 or more, like General Electric said, something like that. So it takes all these spans, and then it uses this sort of span representation. So for example, yeah. So for every span, what it does is it takes the bidirectional LSTM hidden states, the first word and the last word, and it takes that as the representation for the span. So then these span representations using the span heads are used to generate the attention scores, which would give the final representation for this. I think I missed something here. Okay, yeah. So why are we taking a span here? So let's assume that we have a span here, which means it has a starting word and it has an ending word. So the hidden states for each of these here, X star is the hidden state for the span start and end words. What it does is it represents the context to the left and right of the span. So these kind of span representations help us in getting better representations. So the first two terms here give us the context for the left and right of the span, and xi hat represents the span itself, whatever the span is, the group of words that we have, and then we have some additional features that are also being added for this. Okay. Yeah, but the problem is that when we have a text document which has t number of words, the total number of the possible number of spans that could be generated are of the order are of the exponential order, so which is huge. So if we have like 5 words, the total number of spans that can be generated are like 25. So generally, when we're talking about NLP and text, we have huge number of words, which means that would make this really, really big and hard for the computation. So for that purpose, they do some sort of pruning to reduce the number of spans. And so attention is being used here, and it is being used so that it helps in learning the words which are important rather than every other words. These are called head words, as we have seen in a previous example where cat was the head word. Similarly, there will be head words for every example. So here in this sentence, we can see that the words fire and blaze are like the head words. And then there is another approach, the final approach called, which is based on clusters. So what happens in cluster is that when we have a sentence like, we have words like this, we initially form clusters of, clusters like this, which could be of length 1. Cluster 1 has Google, cluster 2 has the company. Similarly, we have 2 other clusters. So this could be the first step. And then we can do cluster merging. So when we know that there are 2 words which are co-referring each other, they both can be clubbed together to form one cluster. So we have cluster 1 and 2, and they are being merged to form Google the company. Now, Google the company form one cluster, Google Plus and the product. So that makes sense. Google Plus is product. So these 2 are being merged together to form another cluster. So finally, we do know that Google the company is one cluster, Google Plus the product is another cluster. But these both together do not really form the cluster because they are kind of different. So previously what we were doing is for every word, we are trying to see whether the words that have come before it are actually co-referents of each other or not. So that kind of mention pair decision is kind of difficult. But when it comes to cluster pair decision, it is comparatively easier. So here, what happens is that we have these mention pairs, and for every mention pair, we have some sort of representation, and that helps in cluster pair representation, which would finally generate the score for the merged clusters. Okay, we have some slides here. This is about evaluating coreference. There are some metrics like MOOC, CEF, LEA, and B cubed. Okay, so I have a blog that I want to quickly go through. I'll do that now. Okay, hope you can see my browser now. So there is this blog by Thomas Wolfe from Hugging Face. You must have heard about Hugging Face. They have been doing a lot with NLP lately. They even got, I guess, they got some good funding as well. So yeah, why is coreference important? Let's say we are building a chatbot, and there is an example conversation like this. The user says, "My sister has a friend called John." And the bot says, "Really? Tell me more about him." And the user replies saying that she thinks he's so funny. So now these sentences seem pretty simple for us, but for the machine to comprehend and understand some of the details in it, it's not really that easy. Because when the user in the second sentence says that she thinks he's so funny, the machine or the program needs to understand that the user, by mentioning she, is actually referring to his sister. So these kind of this is the kind of understanding that has to come from the program. So she refers to the same entity as my sister, so that's one co-reference. He refers to the same entity as a friend called John. So these are the things that the machine needs to understand. So there's something called Vinograd Schema Challenge. So Vinograd Schema was mentioned in the slides as well. So just like we have Turing tests, there's something called Vinograd Schema, which actually tests how good the coreference resolution systems are. And it is believed that if there is a system which is sophisticated enough to get a good score on Vinograd Schema, then that means that we're actually getting closer to proper AI, which is not really easy. So before neural networks, we can see that traditionally the set of features was hand engineered. So something like, we know that the pronoun her is a feminine pronoun. So if we are going by the hand-driven, hand-engineered approach, then there will be rules which say that when there's a pronoun her and there are entities like my sister and my brother, since her cannot refer to a male person, the system has to understand that the word her is actually referring to my sister, but not my brother. So these are the kind of hand-engineered rules. So we have seen in the slides that there are some sort of embeddings that we have for the purpose of coreference. So what we have on left here is a normal word-to-vec word embeddings. As we can see here, there is not much distinction based on gender. We have wife, we have husband, father, brother. They're all being mixed together here. But on the right here, what we see is a trained embeddings. These words, these embeddings are generated from the model that is trained on some coreference annotated data. So here we can see that there is a clear distinction. The words girl, woman, wife, sister, all the gender related words that are, all the words that are related to female are on one side. And then we have on the other side, like dad, brother, husband, these are all words that refer to the male. So there is a clear distinction here, and these word embeddings are generated using a coreference annotated data set. Though these kind of data sets exist and they help us in generating embeddings that can be used for coreference tasks, they're not really perfect. Just like we have a lot of problems with other NLP related data sets, even this data set is not totally flawless. So here is another example. The trophy would not fit in the brown suitcase because it was too big. Now, what exactly was too big here? Is it the trophy or is it the brown suitcase? Even for us humans, sometimes sentences like this can be tricky to properly understand. Now think about a machine that needs to figure out what exactly it refers to. So in the Vinograd schema challenge, the coreference systems or the models that we build or the systems that we develop, they're expected to solve questions like this. So that helps in evaluating these kind of systems. So here is one example. We have the sentence. For each word we are getting the embeddings, and finally we get the scores. So that's about this blog. I actually attended one conference yesterday. It's Amazon AI conference. It had some interesting sessions, but I attended one which was about Alexa. I don't know whether you saw I couldn't find the demo or the demo video for it, but Amazon Alexa has this feature where if you say something to it responds. Like when you ask Alexa how's the weather, it responds. It also has this feature where if you whisper something to it, like instead of saying Alexa how is the weather, if you say something like Alexa how is the weather, like if you whisper to it, and then it also whispers back. So there is this, that was pretty interesting, and I couldn't find a video. Let's check if this is the video or not. I don't know whether you were able to catch the audio of it or not. The user here has whispered something to Alexa, and Alexa, as a response, also whispered. So that was something very interesting. So normally what happens is when the user says something through voice, there is automatic speech recognition that happens. So maybe Alexa also has this whisper detection. So for every user query that comes from voice, it does two things. One, it gets the speech. It does the speech to text conversion. It does the text. It gets the text, And then it also checks whether the user has normally spoken something or the user whispered. So there is also a whisper detection in place. So once it has detected whether there is a whisper or not, and then it gets a response, and if the user has whispered, it also changes its response and speaks as if it is whispering back. So that was quite impressive. Uh, and the talk was also good. I'm personally very interested in voice assistance and like using voice as the mode of interaction. So it was very interesting to see something like this. There were also few other interesting demos, and yeah. So that's what I wanted to discuss today. So are there any questions, or is there anything that you would like to say? Okay, we have Mandar as well now. Hi, Mandar.
Hey, Avinash.
So, did you go through lecture 16?
I did not.
Okay, okay. So, like most of the lecture was about, I mean, the entire lecture was about Coreference, what it is, what are the kind of approaches uh, that we can take. But something that that I would say is something that I didn't know before is that coreference is it's really a tough task to do, because figuring out when we have something like the word they and you have multiple people before, how do we figure out who exactly the word they is referring to? So uh, there were some maybe you can quickly go through the slides sometime whenever you're free. That would give you an idea.
Yeah, I scrolled through a slide while you were speaking. So.
Okay, sure. So there seems to be some overlap with another study group, Fast AI NLP. Yuri was telling me about that.
Yeah, I wanted to ask, maybe would you be able to do this lecture half an hour earlier? Like
Half an hour
start
earlier?
an hour?
Yes, starting earlier is not a problem at all. Maybe we can, I'll post a message in the channel. Yeah, it's better we get started maybe half an hour earlier.
All right, cool. Thank you so much.
No problem. Thanks for joining.
Thank you. Great.
Okay.
So, Avinash, are you working on any projects?
I was working on a virtual assistant thing, but I got something came up and I had to like put it aside for a while. I'll be getting back to that probably in by the end of Jan. But that's the project that I have. What about you?
I think I spent some time trying to understand the transformer, so that's where I am trying to
Good.
dig in.
Sure. So
Yeah.
maybe if you feel that you got a pretty good idea about it, and if you would like to share with us, maybe you can take.
Yeah, actually, some of the resources that were shared, I think by Srinivas.
Yeah, Srinivas. Yeah, they're pretty good. Yeah.
Those are pretty good.
Yeah.
Yeah.
Sure. So, are you also joining Fast AI NLP study group?
I'm not.
Okay.
Yeah, I'm just going to focus on this, and there's also CMUs. I just came across the CMUs course. So.
Yes, that is very good as well. They have both deep learning course and also one course purely on NLP. Are you referring to that same thing?
Yeah, the NLP one.
Yeah, I was actually thinking that once we are done with this, maybe we can start that.
Yeah, just to target the things that I guess we didn't understand very well.
Yeah. Okay. So, anything else that you would like to discuss?
really.
Okay, so I'll be hosting the session next week, and the week after that, I'll not be able to do it, which is on Jan 4th. Yeah, I'll be off on Jan 4th. So again, we'll get back on 11th. So we have one, I'll be there next week, but not on Jan 4th.
Okay. So actually, I just want to bring up, like transformers seem so powerful. I just don't know why this course has focused so much on RNNs. I mean, it seems like everyone has moved on to transformers.
Yeah.
And most of this course still covers
Yeah. So what I felt was that even some of the things that were covered, they didn't really get into the details of it. So I think it's kind of different. Like from FastAI, if you compare, they actually take what's really is working really good right now, and they talk about that, right? So that's what we have seen in FastAI. At least in I haven't gone through NLP, but normally talking about deep learning AI, they actually take Jeremy takes whatever is working really well, and then we get deeper into that. But this course, like it's like they have tried to cover the things that worked well, like 2 or 3 years ago, and then they touched briefly on the things that are working very well right now. Not sure though.
Yeah, it'll be interesting to see whether they completely move on to transformers coming January.
Yeah, maybe they might. Hope so.
All right.
Okay. Thanks, Mandarsh. See you next week, and have a happy weekend.
You too. Thanks.
Thank you.